Okay, we want to do lateral earth pressures. You've seen a lot about them, but I'm going to cover some new things here. You remember that we have like a gravity wall is like a heavy bookend. A cantilever, sometimes called a cantilever wall, is like this kind of bookend. And it's all about the weight. These are both of these are gravity walls. This is very heavy, and it's the weight that keeps it in place. Why? Because there's an active stress there pushing the bookend, and we're relying on friction at the bottom to prevent sliding, and we're relying on the weight of the wall to prevent overturning. So this is all about the weight. The weight creates the friction, and the weight resists the overturning caused by the PA. And this is similar, but this is a cheaper bookend because we're relying on these books here become part of the bookend. So when I analyze it, again, it's going to be the weight of the books sitting on the bottom part of this bookend, and the weight of the books is also resisting the overturning of the bookend. Now, the other thing about it is that this little tail sticking out there gives us a little extra moment arm for that weight, so that helps us as well. So instead of books, we have soil for our earth retaining walls. And if you remember, the active earth pressure is the pressure when the wall moves away from the soil a little bit. So as this bookend moves outward, what happens? We get the active stress there. The passive earth pressure, passive stress, is when the wall moves toward the soil. So if I have a rectangular wall here, and here's soil there and soil there, when the wall moves in this direction, what does it do? It's moving away from this soil, so this is the active zone. It's moving toward this soil, so that's the passive zone. So the passive helps us, right? Because it keeps the wall stable. So one way to look at it is passive is good, that helps us. Active is bad because the active is what's trying to turn the wall over or make it slide. So active is bad, passive is good. It's not, it's just a way to think about it. You want a lot of passive. Passive helps us out. Now, so we have Ka for the active earth pressure coefficient, we have Kp for the passive earth pressure coefficient. But there's one that we don't talk a whole lot about, and that's K0, which is the at-rest coefficient, which will come into play a little bit here. And of course, for all of the Ks, all of the Ks, whether it's active, passive, or at rest, that is the ratio of the horizontal effective stress to the vertical effective stress. So this is the basic. You have to know that. And remember, don't forget the effectives. It's the sigma primes. H equals horizontal, V equals vertical. Now, the at rest, where does that come into play? Well, you look at a bucket of water or a bucket of sand, whatever. If these walls are fixed and don't move, then we get the at rest situation, because remember, we need movement to get the passive or the active. We're moving either away from the wall, away from the soil, or toward the soil. If we're not moving at all, it's at rest. K0 is the at rest coefficient of earth pressure. So if these walls on this bucket are fixed, rigid, then we don't get any movement. So if I take a bucket of water, I apply 100 psf vertically to that. What is the increase in stress? Well, it's going to be a 100 psf in water. When it's water, I put down 100 here, I get 100 horizontally. That's the way water works, right? I press downward with 100, and I get 100 the other way. So that gives me a K naught equal to 1 because the vertical and the horizontal are the same. But if I have a bucket of sand, then what happens? If I apply 100 PSF downward that way, what do I get on the side of this for the sand? Well, people have measured this, for instance, and it comes out to be about half, 0.5. So if I put down 100, I get 50 going that way, approximately. It depends on, well, this is what it depends on. People have found it depends on the friction angle. So K naught approximately is 1 minus the sine of phi prime. So if we know for sand and gravel, if we know what the phi prime is, then we know what the K naught is. So this is an approximate equation, and it's used quite commonly, but it's approximate, not guaranteed. For clay and silt, then what? Well, then we're going to use, people have found that we use the plasticity index, the PI, and the K naught is approximately equal to 0.19 plus 0.233 times the log of the PI. So that's a funny one, but people will use this expression. So, for instance, you may use these in practice. You may see this on the exam. Okay, so this is just a little bit of a review. Find the active stress and the active force, sometimes called the thrust. The active force, thrust, for some reason they use the word thrust on a wall. I'm not certain why, but watch for that little terminology. Thrust is a force. And we're going to use what we call Rankine, which was what we've always used, which is that the Ka is tangent squared 45 minus phi prime over 2. I'm going to show you a different one that's not Rankine, and that's why I'm saying this. So I have dry gravel with a gamma d of 110 pounds per cubic foot, a phi prime of 28 degrees, and you've done this a billion times when we make a table. Sigma v u, sigma v prime, sigma h. It's dry, so that makes your work a lot easier. These are, we have the sigma v, the u, and then to get column 3, it's 1 minus 2. To get column 4, it's Ka times column 3. And to get column 5, it's column 4 plus column 2. So, in a nutshell, that's how you do these. Pause the video here and fill out this table. I've already filled out the 0. All you have to do is figure out what's going on at 8 feet. So just fill in this bottom line. So pause the video here and fill in that line. Okay, filling that in, it's pretty straightforward. You've done this a million times. 8 times 110 for the sigma v is 880. It's dry, so that's 0. Makes it easy. So that becomes simply 880. Sigma h prime is simply the Ka, and since the phi prime is 28, we get 45 minus 28 over 2 for that portion. We end up with 0.361. So that goes into my Ka there, and there's my sigma v there, sigma v prime rather, and we get 318. And then I add the 318 plus that, 0, I used to do it 318. So that is my sigma h, that's my, now I'm going to show you a little, you're going to see this written in textbooks. Oh, let's see, okay, so I want to get the force, sorry. But, so we want to get the force, we take 1 foot perpendicular to the paper. So I'm going to convert this stress, which is 0 at the top, and is 318 at the bottom, and we get this triangle, so we find the area of the triangle, take 1 foot, multiply it by 1 foot perpendicular to the paper. So it's a triangle, so it's 1/2 the base times the height, and then multiplied by 1, I still get 1272 pounds. So that is the thrust or the force. Now, just to let you know, you'll see this shortcut equation for the force to go directly, instead of doing all of this, you can, and then getting the area, you can use this little shortcut equation. The problem is the shortcut equation, I'm just going to warn you, only works sometimes, not and rarely, but you can plug it in. So this shortcut equation is right there, is 1/2 gamma Ka times h squared. And so 1/2 gamma is 110, Ka is 0.361, h is the 8 squared. If I plug that in, then I'm going to get 1270. We got 1272. So in this particular case, with dry gravel, it works. That's pretty much, dry gravel, dry sand, that's pretty much all, the only time it works. And it's got to be one soil. You can't have two soils there. So just to let you know, you will see this shortcut equation written in a lot of textbooks and things like that. You have to be very, very careful with it. To be honest with you, I don't recommend it. Just do this. It takes just a little bit longer. You're guaranteed to get the right answer. But this is a shortcut equation you should be aware of. Again, you'll see it in practice. You would see it on the PE exam. Okay. So do both for this one to get the active and passive forces. And so there's the active and passive coefficients. I filled out the first line, which is all zeros. You pause the video here, fill out the bottom part here. Okay, this is what it looks like. Everything's dry sand. There's the angles. I get for my Ka, I get that. For my Kp, tan squared 45 plus phi prime over 2 gives me my Kp. And the shortcut method, I guess I didn't say it, but for the passive, it's the same thing. It's just I replace Kp with Ka. So it's 1/2 gamma h squared Kp, 1/2 gamma h squared Ka. And you plug those in, you get 5712 and 6300. And if you fill this out, 20 times 120, 0, 2400, then I use my Ka here. I get 571.2. There's no pore pressure, so it's 571.2. And then on this side, we're only down 5 feet, so it's 5 times 120, 0, 600, and then my 4.2 here times 200, 5 times 600 gives me 2520, 2520. So, okay, so then I can get the distribution, 571 here, 2520 there, and I find the area of the triangle, 1/2 the base times the height, 5710. 1/2 the base times the height, 6300. And what do we see? Those are the same, and those are the same. So, shortcut method, but again, it's only dry sand, dry gravel. It's only going to work under those circumstances. Now, does the shortcut work if the pore pressure is not 0? Check it out. Well, here now I have a water table there. So what I want you to do, again, I filled out the first line. You fill out the second line. Try the shortcut method. See if you get the same answer. Okay, so pause the video here. Do this. Okay, so now I have a saturated unit weight of 130, so this is going to be 10 times 130, which is 1300. The pore pressure is what? 10 times 62.4, 624. 1300 minus 624 is 676. The Ka is 0.3. So 0.3 times 676 is 203. Now I add these two together to get this, and I get 827, there is my, I put the 827 here, there is my triangle. I take 1/2 the base times the height, and I get 4134, and that would be pounds, taking 1 foot perpendicular to the paper. And what do I get if I apply the shortcut method? It's 1/2 gamma, 1/2 Ka gamma h squared. And I plug that in, and I get 1950. Well, it's not correct. This is correct, this is not correct. So the shortcut method doesn't work here, so don't do it. Don't use it. The shortcut method does not work when u does not equal 0. Now you can use the shortcut method when there's only one soil and it's completely saturated by doing this. You take the 1/2 Ka gamma prime h squared plus 1/2 gamma w h squared. So gamma prime, if you remember the way we defined it, is gamma prime is equal to gamma saturated minus gamma w, and so it's going to be 130 minus 62.4 times the h squared, this is 10 squared, and then I add 1/2 gamma wh squared. So, and then I get the 4134, and they agree. So the shortcut method works, but only in certain cases. So that's the moral there. Okay, so what about if we have a braced wall? It's one thing that I haven't covered. Well, what's a braced wall? A braced wall is, for instance, when we dig a trench, and the easiest way to stabilize the trench is just put struts across from one side to the other. So that is a braced wall. The braced wall being, these are the braces, the struts that go across. And it's not a gravity wall. And notice that the interesting thing about this, of course, is that it's difficult to get active or passive here. Why? Because the wall is braced across. So how is the wall going to move in this direction? For instance, that wall, when if it tries to do it, it's resisted by this side. Same thing over here. So when I have a braced wall, what people have found is, this active and passive stuff doesn't work because of the way the bracing works. I don't get active or passive. So people have measured this, and so this normal triangular distribution that we have does not work. So it does not work. So when you're in practice or on the exam, you can't use, when you're given a braced wall, you can't use our regular active and passive stuff. So instead, we have to use what people have found, and this is what people have found. They find these distributions, not triangles. None of them are triangles. This one's a rectangle, this is a trapezoid, this is a trapezoid. So you have to use these. Now, this is the distance h right there from the top to the bottom of the excavation. And this is the distance h for each of these. So there's my h, there's my h, etc. This is h. So what you do is, it's quite simple then. It makes your life a lot easier in a way. You just use this. That says 0.65 gamma h Ka, where Ka is the tangent squared of 45 minus phi prime over 2. And that's in sand and gravel. If I have a soft to medium clay, then what? Then you use either 0.3 gamma h or gamma h times 1 minus 4 SU over gamma h. And you use the larger of the two. This is in soft to medium clay. And then we use we just use those distances there, and it's pretty straightforward, so that you can get the pressure easily. So anyway, so hold on. All right, let's do a little problem here, and we want to find the stress distribution in the dry sand soil. So it's an easy soil, and the unit weight is 135, friction angle is 33 degrees. So what you need to do is simply find the stress distribution. So I want to find the stress. It's going to look like that. It's why? Because that was what we had for sand. And so that's how we knew that this was going to look like that. So what I want you to do is to use the diagram and come up with the stress distribution and for this case. Okay, so pause the video. Okay, so what do we got? Well, I find Ka. Okay, Ka is tangent squared 45 minus phi prime over 2. It's 0.295. I simply put that in. This is 20 feet, so I have gamma. So there's the 0.65, there's the gamma, there's the H, and there is the Ka. I get 518 PSF, which means what? Which means that this is 518. It goes straight down like that, and here is the stress distribution. Now, I have my struts here. These are my struts, and I have first strut, second strut. You can figure out what the assumption is, that this wall is very flexible. Okay, so it's generally a sheet pile wall, and it's considered flexible. It's not really, but for the sake of design, you can figure out what the stress, what the load is in that strut, for instance, by taking tributary areas. So if I take this, I assign this region to that strut right there. Now, for the top strut, it would be this area for that top strut, and then this bottom part goes into the soil down below here. To get the load into that strut, just take that area right there for that strut. Now, I realized that I had a little, something's missing here, so I want to fill this in. And that is that this distance here is 0.25 H, and this distance here is 0.25 H, and this distance here is 0.25 H. So so that you can complete these stress diagrams here. Okay, so that's how you handle a braced wall. Okay, another thing that I haven't covered yet is what's called Coulomb earth pressures. Now, I never called the name, but we did Rankine, what was called Rankine. He was the one who did this work, who came up with the Ka is tangent squared 45 minus phi prime over 2. Kp is tangent squared 45 plus phi prime over 2. These are a little bit conservative. That's one of the reasons I will teach them. They tend to be, like I say, active is bad, so they're big on the active side. Passive is good, so they're low on the passive side. So if you overestimate the active and you underestimate the passive, then you end up with a conservative design. But Coulomb came up with a different solution for Ka. I'm just going to cover Ka, and it looks like this, a little more complicated. Now, first of all, what's the difference? Well, one of the differences is that Rankine assumed we had what I'll call a greased wall. In other words, let's just say here's my wall, and here's my soil on this side. And if we have this wall and we put grease on it, and that means there's no friction between the soil and the wall, then we end up with, we can get Rankine. We can get Rankine. That's how Rankine did it. But Coulomb said no, said there's some friction here, which actually helps us. So by assuming some friction there, we can actually get lower actives and higher passives. So Coulomb added that in. He also added the effect of different geometries. So Rankine is a vertical wall with a horizontal backfill. Coulomb puts in these different geometries. So we have an alpha here, and alpha works into the equation there. And we have a theta there, and it works into the equation there. And then we have our wall-to-soil friction angle. And if you remember, we have our soil friction angle, which is phi prime. Normally, delta, often is equal to 2/3 of phi prime. So it's related to, in other words, if I have a wall that's a little bit smooth, then the friction is going to be a fraction of the soil friction angle. So there is a delta. So the delta appears in the equation several places also. Okay, so it's a complicated equation, but it's just, you just have to fight through it. And so here's a problem. So I want you to find Ka using Coulomb, using this geometry. Alpha is 20 degrees, theta is 10 degrees. We're going to use delta is equal to 2/3 of phi prime. For our soil, we've got gamma D, it's a dry sand, 120 pounds per cubic foot. And phi prime is 33 degrees. Okay, so plug it into this expression, see what you get. Pause the video here. Okay, so I like to do these things step by step because it's so complicated. I want to be able to double check it. So I'm not going to go through this, but you just basically just plug them in there, and plug these things in here, and plug all these things in here. Pay attention to the brackets and what is squared and that sort of thing, and what you're taking a square root of, and you get, if you work it all through, you get Ka is 0.4697. So okay, I'll stop there.